afternoon to all. Welcome to the lecture of functional analysis. Today we are taking 52th lecture of the functional analysis. Before going to this lecture, let me just recall what we have taken in the last lecture. Lecture number 51, we have introduced a concept of adjoint operator. Right? Adjoint operator denoted with the symbol of T star, but already we are familiar with one symbol T star, which is actually a conjugate operator defined on n star, rather n star to n star. But due to this another definition, conjugate operator on Hilbert spaces, we have defined it as T star into F or T star F operated on X is F of T of X. This mapping we have proved this to be an isometric isomorphism of BH into BH star reverses the product, preserves the identity transformation. Now, by using the relation between the elements of H and H star, a new transformation or a new operator is defined, which is called as an adjoint operator. And this is what a diagram where I have explained in detail that how this adjoint operator is going to exist, which is denoted by a symbol T star and defined from H to H. And under this mapping, or by using this adjoint operator, it takes one element of Hilbert space to another element of the Hilbert space also. If you have any difficulty, you just please watch my lecture number 51 again on YouTube so that you will get the idea. Next, we have seen the theorem dependent on this adjoint operator, rather proving its definition. It's an important property. That property tells that if T is an operator on the Hilbert space, then we want to prove that there exists a unique operator called T star on H, which gives the property as inner product Tx with Y is equal to inner product X with T star Y. Okay, Tx is just a symbol we have used for T operated on X, T of X. Okay, therefore this whatever T star is being defined or is going to exist is called as an adjoint operator. Therefore, one thing we have to keep in mind that whenever T is defined on H star, this will be a conjugate operator. Whenever it is defined on H, it will be an adjoint operator. Therefore, we have proved stepwise that how this is going to exist and how the operator is unique also. Uniqueness of T star also we have proved. Okay. Then later we have seen that whatever is the relation we are using, the property inner product Tx with Y, which we are writing as inner product X with T star Y, which can also be written as inner product T star X with Y is X with Ty. That is, we can shift this T from first variable to second variable with T star. Also, we can shift this first variable, this T star from first variable to second variable as T. That is, whenever we are going to change the positions of the operator T from one variable to another, then it is going to change the position by T and T star. Okay. Later we have proved an important theorem that T star is an adjoint operation and this T star is bounded linear transformation and every T determines T star uniquely. This also we have seen in detail. I don't want to repeat all the theorems because in detail we have seen. Next, therefore, we have written that the mapping T to T star is called as an adjoint operator on BH into itself. Okay, because this is going to take an operator to its adjoint operator. Later, some properties we have seen that the adjoint operation preserves addition, reverses the product, and it is conjugate linear. One proof I have shown you, and I have told you to do the remaining proofs. Okay, I hope you have completed all those proofs. One more important theorem we have seen is whenever we have T star to be an adjoint operator defined on H, then T double star is T, norm of T star is equal to norm of T, and norm T star T is equal to norm square T. This proof also we have seen in detail. Now let me come to this today's lecture number 52. Before going to proceed to lecture number 52, if students were having any queries up to this, you can ask. Otherwise, I will continue because today there are some 2-3 operators which I am going to define, and today we will complete the syllabus of functional analysis. Okay. From student side, if you have any difficulty, you can please ask me. Otherwise, I will continue with my lecture with some remaining operators. Yes, student side. Now the first operator today we are going to understand is self-adjoint operator. Is self-adjoint operator. Adjoint we have seen in detail. Okay. Now we will have a look to this self-adjoint operator. The name itself tells us the meaning actually. The operator which is adjoint of itself. The operator which is adjoint of itself. Let me write the definition. An operator, T on a Hilbert space H is said to be self-adjoint. Said to be self-adjoint if T star is equal to T. T star is equals to T. Okay, therefore let me recall again. The operator which is adjoint of itself is called as self-adjoint operator. And in the last lecture itself, while studying the examples of adjoint operator, we have seen that zero and identity are the operators which follow this property. Now, here I have shown zero and identity are the self-adjoint operator, and knowing those are the self-adjoint operator, we have obtained by uniqueness of the adjoint operator that 0 star is equals to 0 and I star is equals to I. From this one can easily understand the two examples for the self-adjoint operators are 0, 0 operator and identity operator are the two examples, good examples to understand the self-adjoint operators. Self-adjoint operator. Okay, therefore let us just try to understand some important properties of the self-adjoint operators. Okay, the first property we are going to understand is if A1, A2 are self-adjoint operators, if A1, A2 are self-adjoint operators on Hilbert space H, then their product A1 dot A2 is self-adjoint. A1 dot A2 is self-adjoint if and only they commute. Commute means they are going to commute with one another. That is A1 A2 is equal to A2 A1. This is what one of the important property. Okay. One more we have. Whenever we have T is an adjoint operator, then T plus T star and T star T are self-adjoint. Okay, one can check it very easily. Suppose I want to check T plus T star is adjoint or not. Therefore, what I have to consider? I have to consider the adjoint T plus T star, and by the previous properties, the adjoint operation preserves the addition. Therefore, let me write as T star plus T double star. For T double star, we have already proved as T. Therefore, this is T star plus T, and we know that this is going to be abelian or commuted. It is not. It is going to be abelian under the addition set of all self-adjoint operators. Therefore, I can write this as is equal to T plus T star. Hence, T plus T star is self-adjoint. Similarly, I want to check it for T star T. Let me consider T star T. It's adjoint, and according to this adjoint operation, it is going to reverse as the product. Therefore, this is T star. Okay, I'm going to change the order in the adjoint. And the first one will be taken later. It is having only one star already. Therefore, let me write two different double star. Therefore, this is T star T. But again, as I told you, this is commutative. Therefore, this is T star. So whenever we have T to be a self-adjoint operator, T plus T star and T star T are the self-adjoint operators. Okay. Property number 3 is if yes is set of all adjoint operators. Set of all adjoint operators in VH, then S is closed linear subspace closed linear subspace of B of H, and hence or therefore hence S is real Banach space. S is real Banach space containing identity transformation. Containing identity transformation. These are the important properties we want to understand regarding the self-adjoint operator. Okay, one more. Number 4, property number 4 is if T is an arbitrary operator on Hilbert space H, then T is equal to 0 if and only if inner product Tx with y is equal to 0 for all x, y belongs to H. Okay, as we are saying that for all x, y, this inner product is 0, therefore the only possibility that T itself will be 0. T itself will be 0. Okay, or one can write one more property if T is an operator on a Hilbert space H, then inner product Tx with x is equal to 0 if and only if T is equal to 0. This is just like a subcase of the previous statement. This is like a subcase of the previous statement. Okay. Next, an operator T on complex Hilbert space is self-adjoint if and only if inner product Tx with x is real for all x. Okay. Actually, these are the properties one can take with the proof also, but according to the syllabus question paper pattern, we are taking only the statements. Okay. Next, number 2, we will define a order relation. What is order relation? If S is the set of self-adjoint operators, comma, we can define order relation. Denoted by the symbol called less equal on yes as. What as? A1 less than or equals to A2. Comparison we are defining if inner product A1x with x is less than or equals to inner product A2x with x for all x in H. Means whenever we want to compare two self-adjoint operator with this less equal symbol, then A1 is less equal to A2 if and only inner product A1x with x is less than or equals to inner product A2x with x. Okay, let us just go for the properties. What are the properties? Okay, the real Banach space of all self-adjoint operators on Hilbert space is a poset, partially ordered set whose linear structure are related by following properties, or given by the following properties. The first property is A1 less than or equals to A2, then A1 plus A is less than or equals to A2 plus A for all A in yes. First property. Second, this is with respect to addition rather. Now we will go for scalar multiplication. A1 less than or equals to A2 and alpha positive, then alpha A1 is less than or equals to alpha A2. Alpha A1 is equals to less than or equals to A2. This is what about order relation. Let me go for third definition called as positive operator. Called as positive operators. Okay, now this property is specially for the self-adjoint operators. This property is specially for the self-adjoint operator. The definition is a self-adjoint operator on H is said to be positive if A is greater or equal by 0 in the order relation. This means that inner product Ax with X is greater or equal by 0 for all X in H. You will write that is. What is the meaning of A greater than or equals to 0? Inner product X with X is greater or equal by 0 for all X in H. And here I can say very clearly identity and 0 are positive operators. Okay, now let us go for the properties. Number 1. If T is positive operator, then I plus T is non-singular. Okay. Property number 2. T star and T star T are positive operators. T star and T star T are the positive operators. Okay, these are some 2 properties we have studied. Let me go for next 4th definition. The 4th definition is normal operator. Normal operators. Okay, what is the condition for the normal operator? As operator is said to be normal if it commutes with its adjoint. Let me write. Yes. Let H be reverse space and N be an operator defined on or belongs to B of H and N star be the adjoint of N. Then N is said to be normal operator if N star is equals to N star N. And N star is equals to N star N. That is, if it commutes with its adjoint. If the operator commutes with its adjoint, then it is called as normal operator. Okay, therefore the first property we will follow is every self-adjoint operator is normal. Every self-adjoint operator is normal. Why every self-adjoint operator is normal? Because if we have a self-adjoint, since T is self-adjoint, we have T is equal to T star. Therefore, how can I write T star? Let me replace this T by T star by T. Therefore, I can write it as T star T. Therefore, every self-adjoint must be a normal operator. Every self-adjoint must be normal operator. Property number 2, the limit n of any convergent sequence nk of normal operator is normal. Nk of normal operators is normal. Limit of sequence of normal operators is normal operator. Property number 3, the set of all normal operators on Hilbert space H is closed subset of B of H, which contains the set of all self-adjoint operators. Why it contains the set of all self-adjoint operators? Because all self-adjoint operators are the normal operators. Self-adjoint operators and closed under scalar multiplication. Closed under scalar multiplication. Okay. Property number 4. If n1, n2 are normal operators on H with property that either commutes with the adjoint of other, then we have n1 plus n2 and b n1 dot n2 are normal. Okay, here I just want to clear the word that either commutes with the adjoint of other. Okay, that is, if we have say n1 and n2 are the normal operators, then n1 commutes with the adjoint of remaining. That is, n1 commutes with n2 star. Therefore, I can write n1 n2 star is n2 star n1, and suppose I will take with n2, then n2 commutes with the adjoint of n1. That is, n2 n1 star is n1 star n2. Okay, with this property one can say that n1 plus n2 n1 dot n2 are normal operators. Property number 4, an operator T is normal if and only norm of n star x is equal to norm of nx for all x in H. Next, if n is normal, here I should write n. An operator n is normal. If n is normal, then norm of n square is equal to norm square n. Norm of n square is equal to norm of n square is equal to norm square of n. Okay. Property number 7. Any arbitrary operator T and its adjoint T star on Hilbert space H can be expressed as T is equal to T1 plus IT2 and T star is equal to T1 minus IT2. That is, it looks like a complex number and its conjugate, where T1, T2 are self-adjoint operators. Self-adjoint operators. Okay. Next definition we will go. 4 we have completed. Number 5 we will write. Number 5 we will write real and imaginary part. That is, if definition is T is represented as T1 plus IT2 and T star by the previous theorem property, right? Here we have written. And T star is equals to T1 minus IT2. Then T1 is called a real part of T. Is called real part of T, and T2 is called imaginary part of T. T1 is called real part of T, T2 is called imaginary part of T. Okay, therefore we will write one more property taking this real and imaginary part for normal operators. That is, if T is an operator on a Hilbert space H, then T is normal. T is normal if and only its real and imaginary parts commute. Real and imaginary parts commute. Okay. Next, number 6. Number 6 is unitary operator. Unitary operator. Definition is an operator. U we are using. For n normal we have used n. For unitary we are using u. An operator on a Hilbert space H is said to be unitary. Is said to be unitary if u star is equals to u star u is equals to identity. And if we observe very carefully, the first two properties gives us the normal operator. That is, every unitary must be normal. Okay, every unitary must be normal. This is what a condition for the unitary operator. Okay, any doubt till this, students? If you have any doubt, you can ask me. Unitary operators. Okay, we have a property, an operator T on a Hilbert space H is unitary if and only it is an isomorphism. It is an isomorphism of H2 itself. H2 itself. Okay, this is an important property we have. Okay, next and the last is projection operator. Projection is the mapping we have seen, we have studied in detail, and we have defined it on Banach spaces and in the Hilbert spaces also. In the Hilbert spaces, we have seen by orthogonal decomposition theorem that how this is going to give us projection for every orthogonal decomposition. Okay, therefore there are some 1 or 2 important properties regarding projection operator. I will just mention the properties. If P is the projection on a Hilbert space H with a range M and null space N, then M is orthogonal to N if and only P is self-adjoint. P is self-adjoint and In this case, we will write n is equal to m per. That is, n is orthogonal to the whole space n. Next, if a projection P on a Hilbert space is an operator P on H such that P square is equal to P and P star is equals to P. Okay. Property number 3. If P is a projection on closed linear subspace M of H, if and only if I minus P is a projection on M per. Okay, see what an interesting property it is. Next, property number 4, if P is the projection on closed linear subspace M of H, then X belongs to M if and only Px is equal to X. If and only Px is equals to X. Property number 5, if P is a projection on closed linear subspace M of H, then Px is equal to X if and only norm Px is equal to norm of X. This is property number 4, 5. Now let me just write property number 6. If P is projection then projection on H, then P is positive operator. Next, number 2, 0 less than or equals to P less than or equals to identity. Number 3, norm of P of X is less than or equals to norm of X for all X in H. Number 4, norm P is less than or equals to pi. These are the some of the important properties I have mentioned today for all those operators. Okay, next definition number 8. Definition 8, invariant operator. Invariant. What invariant tells us? Let P be an operator on Hilbert space H and M be closed subspace of H to start. M is said to be invariant under T if Pm is contained in M. That is, if the image of this closed linear subspace is contained in M itself, then we say that M is invariant under T. M is invariant under T. Okay. One or two properties we will take here. Property number 1, a closed linear subspace M of a Hilbert space H is invariant under the operator T if and only M per is invariant under T star. M per is invariant under T star. three more properties we have. I just suggest students to just go through those 2-3 properties remaining. Therefore, here I can declare that the syllabus for functional analysis is completed. If students were having doubt regarding any of the topic we have taken, starting from the first lecture to lecture number 52, you can just ask me. Okay. Thank you for watching the lecture.